system. See how long this one is? Oh yeah, we're watching this for sure. Let's get it, guys. Now this is the tricky part is, hold on guys, we might not be doing it this way. Can I set my screen audio without it sounding like I'm in a thing? I don't know if I can. Mic check, mic check. Mic check, mic check. I didn't even think about that. Shit balls, man. Let me just test this out and see how bad it is. I know you guys can't hear it, so hold on, give me a second.
What a blockchain is. For the purposes of this discussion, it's a list of records linked using cryptography. A block is a cryptographic hash of the...
Can you guys hear her? And do I sound like I'm in a tunnel right now? It's so stupid. I can't even watch my own live. I can watch it on here. Okay. All good? You can hear her too? Let's go, baby. No way. No way. All right, now the question is, can I zoom this in and transition to that same screen? Oh, this is going to be awesome if we can hear this.
Previous block and some time. What does that mean? What is a smart contract ecosystem? So we have a private blockchain and a public blockchain that work together. You can use one or the either or both, and they're both designed to have smart contracts sit on top of them and run. And so unlike some of these other smart contract platforms that may have been designed as a thought experiment, or maybe some guy was like, maybe I can write a virtual machine in a weekend, and then people accidentally adopted it and now it's trading billions of dollars of currency. We were designed from the ground up to be designed for users and people to actually be able to know that what they intend to happen on the blockchain is what they're going to get. So before, we all know what a blockchain is, but in case you go to business school here and you wandered in and you don't know what a blockchain is, for the purposes of this discussion, it's a list of records linked using cryptography. A block is a cryptographic hash of the previous block and some timestamp and some more stuff. So basically it's an append-only ledger. It's a type 1, type 2 enforced database system for those of you with data engineering backgrounds. So it is resistant to modification of data. You can only add new things, and you can upgrade things if the system lets you do it, but you can't ever go back and change something. And this is why blockchains are so interesting. So in private blockchains, only the people that are allowed to access the system can come in and make modifications and see what's going on. In a public blockchain, and this is what was truly novel about Nakamoto consensus in the first place, is that you can have this idea of a ledger that people can't come in and screw around with and totally mess up, but that everyone can contribute to. So popularizing this idea of smart contracts, you can have code that is replicated on all of the nodes of a blockchain, which then allows people the potential to have distributed applications, which, when you think about it, instead of having to pay Amazon to spin up an EC2, which is really just a server in Virginia, in order to run your app, you can, by paying whatever the gas fee is on Ethereum these days, have your code run by hundreds, if not thousands, of people all around the world individually. And like my friend Felix in Berlin, who has a mining rig in his closet, will run your code. And so nobody can take down Felix's rig and Amazon EC2 in Virginia and all the other thousands of people that are running your thing, which is why distributed applications are potentially so cool. Okay. So what is the Kadena ecosystem? I use the word ecosystem. So we have a smart contract language that I'm going to just come out and say is the safest, the simplest, the best smart contract language. And it's fully open source. Anybody can go and use it. Right now, we're on version 2.8, version 3 coming soon. We have, I'm going to go in and talk about Pact and why I think it is the best. And we have scalable BFT, which is a fully BFT and not like just a database with fancy permissions on top of it. And it actually scales. And I'm going to go in and talk about some other private blockchain companies and what they're working on and how I think we're different. And then we also have a proof of work public blockchain. And all of these pieces fit together so that if you came along and you were like, I really want to make, let's take, Tarun talked about tokenized real estate. I really want to make a tokenized real estate application where I can have data about who owns what pieces of properties, but I don't want that exposed to the public. I want that on a private blockchain, but I want to be able to sell those tokens in public on a public network, and I want it all connected, all in the same system. That's what we do. This thing, okay. So we're a base protocol, sort of like all of these other smart contract-based protocols, like Ethereum, like some of these others. I'm actually being a little disingenuous with this graphic because I have both private blockchains and public blockchains up here at the same time. But so on the left, you've got other things that are proof of work. And say what you will about proof of stake, it has the potential to be really cool, but nobody has proven yet that it works. As opposed to Bitcoin, which has had 10 years of people trying to kick it over, and it's still standing. So we believe that proof of work is, if you can do it more efficiently, proof of work is still going to be the way. So other projects that are designed for scale, we've got Hashgraph is up there, Definity is up there, but they're not proof of work, and they don't have smart contract systems unless something has changed since the last time I went around and looked at what they're doing. Other smart contract platforms like Hyperledger, not necessarily scalable to the same degree that some of these other projects are. So we've got all of these things that I think are important. So I'm going to go in and talk about all of these things: Pact, scalable BFT, Chainweb. I don't have a lot of time, so I'm going to move a little quickly, but then we can have questions afterwards. So Kadena ecosystem: reliable code that checks itself, stable, secure networks that resist censorship and attacks, and applications that reliably scale. So first, Pact. Why I think it is the best smart contract language. So first, what is a smart contract? This is the idea that you want your app to be run by Felix in his GPU cluster in Berlin, as well as thousands of other people. So execute the terms of a contract. I want to transfer some value from me to some other person. And this chunk of code is included in a blockchain transaction. And it's rerun by every validating rerun by every validating node upon receipt of the block. And everybody on the blockchain can see what you're doing. Smart contracts allows you to distribute code and in a censorless way on a public blockchain. On a private blockchain, it's a way for you to put transactions out there that you can broadcast to all the members of the network, and no one can say that you didn't say what you actually said. So, smart contracts, if we can figure out how to really do them right, have the potential to be really cool. Like, if you've ever tried to rent your apartment to somebody or like buy something on Craigslist and you're like, I want this thing, but I don't know if it's gonna work and I don't wanna send you the money until I know whether the thing works, like all of these things that actually happen in real life, escrow transactions without somebody in the middle where you both have to sign off on the thing. Tokenized real estate assets that settle quickly with a little overhead. There are a bunch of illiquid assets out there that people want to buy, but you can't trade them because there really aren't markets for them, or they can only trade during the day, but they can't trade at night, and there's an arbitrage opportunity. There's a whole world of things that we could do out there if we knew that smart contracts weren't going to suck. Because right now, smart contracts suck. They just do. You've got, like, I'm going to go in about, like, really why they suck, but people can't expect that the thing that they intend to happen is going to actually happen when they put smart contracts on a blockchain right now. So, for example, I'm just going to pick on Solidity because it's easy to pick on Solidity because everybody hates Solidity right now. It has a bunch of flaws, and some of it aren't its fault, some of it's the EVM's fault, but let's just roll it into a whole ball and say that it's the EVM plus Solidity. There's a whole bunch of bugs in the Ethereum virtual machine. And right now, if you have a bug that's out there, everybody can see it, you can't change it, and it takes a massive consensus of all of these people to say, oh, we're going to hard fork the network to fix this thing that is broken that everybody can see is broken. It's a huge mess. And right now, if somebody has a smart contract and they compile it and they stick it onto the chain, you don't know what that blob of code is. It's impossible to check. And then you have, anyway, let's just start talking about hacks. DAO hack, parity wallet hack. Both of these things are well-recognized problems. This is why people can't trust smart contracts right now. It's, you know, the DAO hack was a recursion bug where somebody could go in and they could hit the wallet and they could ask for money and they could come back and they could keep hitting it for more money before anybody could go in and actually reconcile the account. And then parity wallet hack, you had, you know, because gas is expensive on Ethereum and nobody wanted all of the code to actually be in the contract, you had a call to another smart contract, except that somebody deleted that smart contract and now nobody can get their money out of their parity wallets anymore. So why would Pact have fixed these things? So Pact is Turing incomplete on purpose because we don't want recursion attacks. We don't want you stuck in an infinite loop burning up all your gas. And if you're trying to do something for which you would need recursion, like running Dijkstra's algorithm to find the shortest path between New York and LA, you don't do it on a blockchain. There's no point in doing that on a blockchain. What you need to do is you take it off chain and then you do your computation and then you put it back on the blockchain. So Pact recognizes this fact that Turing incompleteness on a blockchain is dumb. So because we are Turing incomplete and we've stripped out a bunch of other stuff, we also have a full formal verification suite for Pact, which means that you can, in our annotated language, write in, like, prove that this field doesn't ever go below 0. And it will prove in the infinite space of possibilities of things that people could shove in there that it will never go below 0. And so this is, Tarun talked about multiple kinds of safety. And this is the kind of safety where you know that what you're intending for your code to do is going to actually do. But just on the off chance that the code doesn't do what you want it to do, you can actually fix it, because in Pact smart contracts, there's abstraction between the address of the contract and the name, which means that you can rename your contract and say, like, version 2, whoops, that was a problem. Pact smart contracts are upgradable. And you can actually read Pact code. It's not like some sort of convoluted JavaScript. This is the hello world contract for Pact. It's 15 lines, and you can just read it. It makes sense. It tells you exactly what it's doing. You're defining some keys, you're defining some data, you're defining a function, and then it goes. If you tried to do this in Hyperledger, it's 150 lines to do this same thing, because you have to handle all these other abstractions underneath and define a whole bunch of calls, and Pact just deals with that stuff for you. So that's why I think Pact is cool. Moving forward, we have other things that I also think are cool. And so let's start. Private blockchains. People think that private blockchains maybe aren't cool because they're more into crypto stuff. But bear with me here. I think that actually, in the context of even people that want to do public applications, private blockchain can still be cool. So this is a world in which you have a walled garden, and only the people that you let in can see your stuff. And why would you use a blockchain instead of a database? You have non-mutable transactions. You're basically forcing people to use a type 2 database system. And you can't go back and change them because of this whole cryptographic hashing thing. You can't go back and change old records without totally screwing up the whole thing. Then, because you have to sign each transaction, you have strong attestation of who put what thing on the ledger. And then you can just simply replicate data very quickly. So you have the consortium model that everybody's like, oh, you know, this consortium of banks is going to share data between competitors. So there's that one. But then also, if you have a company that has nodes across multiple countries, then you can also have, you know, your Asia node and your US node and your Europe node, and they can very quickly replicate data across them without having to worry about disaster recovery. And then there's also, we're working on with another company for a tighter auditing chain where you can have third-party auditors submit data and you know who did what and when, and you can actually track that stuff down. So as part of a public application, private blockchains can be used to do interesting things in terms of taking things off-chain. So right now, where you have an oracle on a public blockchain where it goes who knows where, doing who knows what with what data, if you connect a private blockchain to the public blockchain with the Pact channel, you can actually prove that the information that happens on one side happens on the other, but you don't have to necessarily share it. So that's their whole hybrid blockchain. You can have public and private at the same time. So other private blockchains, some of them have unsafe development environments because they're on the EVM. It's not their fault. Some of them aren't really blockchains, like Corda. They're totally upfront about the fact that they're not a blockchain, but they use the word blockchain because it's sexy and it sells. Axoni, I mean, all these people are way more successful than we are in that they have bigger clients and more contracts, so I don't feel bad picking on them. Axoni doesn't have an open source smart contract language, although if you go to their website, it does say committed to open source, whatever that means. Or you can try to use Hyperledger Fabric, and it's not going to work past 8 nodes. If anybody's ever figured out how to make Fabric go past 8 nodes, call me, because I would love to figure out how you did it.
That's very important. Simran, that's very, very important. The Byzantine fault tolerance. Let me explain that to you because it'll make that make a lot more sense to you.
Computers.
So what your Byzantine general fault tolerance is this is Cadena uses the BFT as well. A lot of chains do. Proof of stake chains do. They'll explain it here.
Such a technology allowed the creation of trustless economic systems, where borderless financial transactions could be executed without the need for intermediaries. Since traditional banking and payment systems are heavily dependent on trust, cryptocurrencies are now being adopted as a viable alternative because they rely on blockchain technology and are used within trustless systems. The participants of a cryptocurrency network need to regularly agree on the current state of the blockchain, and that is what we call consensus achievement. However, reaching consensus on distributed systems in a safe and efficient way is far from being an easy task. So, how can a distributed network of computer nodes agree on a decision if some of the nodes are likely to fail or act dishonestly? This is the fundamental question of the Byzantine generals problem, which gave birth to the concept of Byzantine fault tolerance, sometimes referred to as BFT. The Byzantine generals problem was conceived in 1982 as a logical dilemma that illustrates how a group of generals may have communication problems when trying to agree on their next move. Imagine that each general has its own army, and each group is situated in different locations around the target city. The generals need to agree on either attacking or retreating. It doesn't matter whether they attack or retreat, as long as they all agree on a common decision. So, we may consider the following requirements. Each general has to decide and vote on either attacking or retreating. After the vote is made, it cannot be changed. All generals have to agree on the same decision and execute it in coordination. However, they are only able to communicate through messages, and the central challenge of the Byzantine generals problem is that the messages can get somehow delayed, destroyed, or lost. Even if a message is successfully delivered, one or more generals may choose, for whatever reason, to send a fraudulent message to confuse others, leading to a total failure. If we apply the dilemma to blockchains, each general represents a network node and they need to reach consensus on the current state of the system. This means that the majority of participants within a distributed network have to agree and execute the same action in order to avoid failures. What is Byzantine fault tolerance? Byzantine fault tolerance is the property of a system that is able to resist the class of failures derived from the Byzantine generals problem. In other words, a Byzantine fault-tolerant system is able to continue operating even if some of the nodes fail to communicate or act maliciously. There are multiple ways of building a Byzantine fault-tolerant blockchain, which are related to the different types of consensus algorithms. We can define a consensus algorithm as the mechanism through which a blockchain network reaches consensus. The algorithm used by Bitcoin is called proof of work and is one of the most common implementations. While the Bitcoin protocol defines the rules, the consensus algorithm determines how these rules will be followed, for instance, during the validation of transactions. The concept of proof of work is older than cryptocurrencies, but Satoshi Nakamoto developed a modified version that enabled the creation of Bitcoin as a Byzantine fault-tolerant system. Although proof of work is not 100% tolerant to faults, it has proven to be one of the most secure implementations for blockchain networks and is considered by many as one of the most genius solutions to the Byzantine faults. Securing these systems is an ongoing effort, and the existing consensus algorithms are yet to overcome a few limitations, but the potential applications are certainly inspiring widespread innovation.
Makes sense? You guys with us so far? That was a really good question. Who asked that? There you go. Simran's listening. That's what I like to hear. Is exactly what you guys should be doing. You guys hear something like that. What is Byzantine fault tolerance? You have to know that, right? What does BFT stand for? These are the things that are going to separate you. You know, when you're looking at other blockchains, you can actually analyze and learn and understand these things. Nice job, buddy.
So, scalable BFT integrates with the public blockchain Chainweb, provides Pact open source protection. So you can use Pact on top of scalable BFT. And then it has a true BFT consensus mechanism. It's not a database, it's actually BFT. And it scales up to, so far our sims can run on the old version of Pact. We haven't tested the new version of Pact yet. Up to 200 nodes, you're still getting 8,000 transactions a second. So if you want to try Scalable BFT, it's on the AWS Marketplace, and you can go download it and try it for free. Last piece, I know I'm running out of time, but I'll keep talking fast. Chainweb. This is my favorite part. This is the part on which I work the most. So our proof of work technology for a public blockchain. Chainweb is a protocol that uses Nakamoto consensus, because 10 years later, it's still kicking despite everyone's attempts to hack it and take it down. And if we can figure out how to use proof of work and do it in an efficient way, in a way that scales, then it's worth trying to do. So Chainweb takes proof of work, and we have many different chains. All of them are running the same Nakamoto consensus, all running the same hashing algorithm, and they share data with each other, which gives us the ability to do high throughput while still getting to use proof of work. So we get higher throughput and higher security and greater decentralization without having to change the amount of energy that you're putting into the system. I give an hour-long talk just about this consensus mechanism. It's on the internet. I don't have time to do that whole thing today. If you want to learn more about it, go listen to that. But basically, each chain is an individual ledger that maintains its own state. And then if you want to transfer money from one chain to another one, you do it with simple payment verification. So all of the chains are equal. There's no hub. There's no main chain. They all have their own ledger and maintain their own state. They cross-reference each other by, if I finish a block on this chain and you finish a block on that chain, then we swap the proofs of the blocks we just finished and include them in the next block. Then miners mine the entire network, and users transfer money from chain to chain. And really, that's going to be totally abstracted away in when users interact with Chainweb on a casual basis. It's just going to be, I'm paying this person over there, and it handles having to transfer from chains, and it's not going to be a big deal. So the Chainweb really as a protocol can be applied to any braid size. It could be a potentially very large network if there's demand for such, but obviously bandwidth increases the more chains that you add, so we're going to wait to make it bigger until there's demand to do so. Oh, I missed a point. The graph structure of Chainweb is fixed, so that each time you want to change it, you have to hard fork to a different configuration. This is what allows us to get the most efficient way of transferring information across the network. You can have a fixed graph structure that has a maximal degree diameter solution so that you can propagate information efficiently. It's not an arbitrary DAG. Arbitrary DAGs have this potential to bottleneck, and you might hear arbitrary DAG projects say like, oh, we get one.
Sorry guys, I didn't catch that part. Hold on.
So the Chainweb really as a protocol can be applied to any braid size. It could be a potentially very large network if there's demand for such, but obviously bandwidth increases the more chains that you add, so we're going to wait to make it bigger until there's demand to do so. Oh, I missed a point. The graph structure of Chainweb is fixed, so that each time you want to change it, you have to hard fork to a different configuration. This is what allows us to get the most efficient way of transferring information across the network. You can have a fixed graph structure that has a maximal degree diameter solution so that you can propagate information efficiently. It's not an arbitrary DAG. Arbitrary DAGs have this potential to bottleneck, and you might hear arbitrary DAG projects say like, oh, we get 1 billion bajillion transactions per second, but that's with all nodes communicating equally across the network with even distribution, which in real life doesn't actually happen because people want an asset that's only traded on that, or this gets slow and everybody bottlenecks over there. And so fixed DAGs have the most efficient way of transferring information across the network. You can have a fixed graph structure that has a maximal degree diameter solution so that you can propagate information efficiently. It's not an arbitrary DAG. Arbitrary DAGs have this potential to bottleneck, And you might hear arbitrary DAG projects say like, oh, we get 1 billion bajillion transactions per second. But that's with all nodes communicating equally across the network with even distribution, which in real life doesn't actually happen because people want an asset that's only traded on that. Or, this gets slow and everybody bottlenecks over there. And so fixed DAGs have this structure that can be maintained in a way that's safe and is not arbitrary. So this is a sample of a 20-chain braid of Chainweb. So for example, if you finish a block on chain 2, then it broadcasts to chains 1, 3, and 16. So what are we working on? We are launching Chainweb soon. Testnet happens the end of next month. Mainnet, I'm going to say this year. We have more optimistic deadlines, but I'm not going to say them in front of anybody else. Finish Pact. We're almost feature complete with everything that we want to put into Pact. We right now have verified interfaces, which is basically an ERC20 that checks itself to make sure that it was implemented correctly. And grow our developer community. We are doing that. We are trying to go out and get people excited about Pact as I am. Then launch our POCs and partnerships. So right now we're working on some of these private and hybrid private and public blockchain projects. We completed a pilot for a health insurance company that was working on sharing provider data. We are working with an insurance company for better auditing, talking to a construction company about supply chain, real estate tokenization projects, and we're also working on this project that I'm super excited about called Remedy that does vaccination tracking. And right now they're doing it overseas, but they want to come into the United States and do a health data tracking project on US soil, which means they're going to have to follow HIPAA. And basically that's something that you can only do with a blockchain technology that allows you to upgrade your smart contracts. And so they're using Pact, and they're going to use the hybrid smart scalable BFT and hopefully Chainweb system. And yeah, so that's what we've got going on.
Man, I learned so much that like I have no freaking clue. Hey, have a good night, Drew. Later, buddy. Yeah, get some sleep, man. Keep stacking that K, buddy. Let's just focus on Monica tonight. She's killing it, man.
I'd now like to welcome Monica Quaintance to the stage. She will talk about technical developments of permissioned blockchains. Monica.
This is why Cadena lost all their marketing.
Thanks so much.
They lost Monica. What the F, man? Good thing they got Paul in place now, because Paul seems to be like he's picking up right where she left off.
Much for having me. I'm actually going to do a tiny bit of a bait and switch. I am going to talk about permission blockchains, but I'm also going to talk about how they can interact with public blockchains in a structure that we're calling hybrid blockchains. So let's get into it. So I work for a company called Cadena, and Cadena, the whole idea behind our entire stack is that it should be easy for you to be able to develop an application for whatever you need to do on blockchain. This goes back to Dan's whole idea of like everything is super complicated and you don't have scalability and you don't have interoperability and none of these things work. But instead of stapling a whole bunch of different technologies on top of each other, we've crafted a single technology solution, and hopefully people are going to use it to create really awesome applications that allow you to hook into both permissioned and public blockchains at the same time. So this whole idea is that smart contracts could be great for business if people knew that they could trust them. And so far in smart contract land with Ethereum and all of these other projects that have had smart contracts so far, you have a lack of trust in that whole ecosystem. And our speculation is that because many of these technologies were originally created as thought experiments or research, that they weren't crafted for business use cases in mind. So we came out of the JP Morgan Blockchain Research Labs, and the whole idea behind Cadena is that you should be able to use these technology for business in a way that you can trust. So blockchain for like 30 seconds. Remember, you have blocks. They're linked using cryptography. And the important part here is that when you have a block that contains information, it contains a hash of previous history, which means you can't go back and modify your existing transactions. This is why people like it for auditing, people like it for tracking transactions. And when you have a blockchain, your information can be ownerless if you want it to be. And whether that means you have a consortium model with competitors where you don't want to have your competitor owning your data, or whether you have a public blockchain and you want it to be completely ownerless. This is one of the fundamental
Does it bother you guys?
Why
We can skip it if you want.
blockchain over, say, a database. So smart contracts. In a permission system, private blockchain, only users with permission can actually see what's going on. In a public blockchain, anyone can replicate. And you can imagine a world in which you would want an application where you would want to have your cake and eat it too. You would want to be able to have private data that you know that not everybody is going to be able to see. But you also would want to be able to go out and access the kind of high liquidity, fast transaction settlement, massive number of potential customers, borderless transactions that you get from public blockchain. So if you could have a system that could give you both, that's what we're trying to build here with Cadena. So I'm going to go through the 3 elements of our stack and then give you an example of one of our clients and why they are using that particular part of the stack. So we have a public blockchain. We launched testnet in March. And it's a proof-of-work-based blockchain, but it's also a scalable proof-of-work-based blockchain. We're basically the only company out there that's building a new proof-of-work chain that has a different scalability mechanism. Everybody else has decided that they're going proof-of-stake. We're just super old school in this regard, and we think that proof-of-work just works. Permission blockchain is called Scalable BFT, and it's in the same family of Tendermint and these other BFT-based systems where you have a voting mechanism. Smart contract, we have our own smart contract language, and this is really the special sauce of what's going on at Cadena. The idea is with Pact that you shouldn't do things on a blockchain that aren't safe to do on a blockchain, and I'll give you some examples of that coming up. In terms of the scope of other people in the world doing blockchain things, we have the same security of proof of work as your Zcash and your Bitcoins. We have smart contracts like Hyperledger and Corda, and we're designed for scale like Dfinity and Hashgraph, but we have all 3 of those things all together all at the same time. All right, so smart contracts. Why would you even want to do smart contracts in the first place? For smart contracts, if you can do them correctly, they're not really a contract at all. They're more like a charter, like a code of governance. And if you could have a smart contract that actually updates itself to follow the business logic as it changes, as it migrates, then you could deeply fulfill the intent through code. And so that's what we're trying to do with bringing smart contracts to business. And so Pact is our smart contract language. And originally, the guy who wrote the first version of our smart contract language, our CTO, Stuart wrote a trading system for JP Morgan that allowed traders to take the ideas that they were thinking of in terms of trading algorithms and turn them into code. We're taking this idea and bringing it to smart contracts. So if you could do things with smart contracts that you actually trusted, then you could have things like multi-party escrow, and you don't have to have somebody in the middle. You can tokenize assets and settle them all over the world without having to worry about overhead and clearinghouses. You don't even have to trade when the markets are open, because there are no markets anymore. You can have APIs that transfer all kinds of information and have data payloads and money payloads inside of them. But nobody trusts smart contracts right now because there have been a bunch of bugs and exploits. like the DAO hack, which drained a bunch of ether because there were recursive calls inside of a smart contract, like the parity wallet problem on Ethereum, where there was a central smart contract library that contained everybody's information and somebody deleted it, and so now nobody can get to their money anymore. You wouldn't ever have these in an enterprise system. None of that would ever fly, which is why we've built an enterprise-grade smart contract system. And it doesn't allow you to do stupid things. So we have a client right now that's using Pact to actually put patient data on a ledger. And the idea here is that you want to put patient data on a permissioned blockchain, and you want to be able to go in and modify it. That's why Pact is the smart contract language that they chose for this project, because unlike Solidity, say, where you can't go in and modify your smart contracts, you can upgrade a Pact smart contract. And I don't need to tell you technically why you can do that. You can just take that on value, and then if you want to talk to me afterwards about how it works, we can do that. And so our client is using patient data to anchor your information, and then they're doing attestation of vaccination on the public network. So this is an example of a hybrid blockchain application. The permission part of our stack is Scalable BFT, and Scalable BFT is a blockchain that is designed to scale on its own as a permissioned blockchain. It's basically Tendermint that makes some assumptions about how your network functions, and then if it fails back to Tendermint. And why you would use a blockchain for your private application instead of a database, blockchains allow you to have data sharing automatically, replicating. And you can have every transaction that goes on get signed by somebody. So imagine that you have some auditors and you have some third-party people that are involved in your, say you have an insurance company. That's a hint. I'm going to tell you about our insurance company client later. You have an insurance company and you have some auditors for your insurance company. You can have the auditors sign transactions as you put them on the chain, so then you know who and when made these data insertions into your project. So Scalable BFT works natively with Pact, and it scales up to a heck of a lot of nodes automatically, more nodes than you would ever really want for a private blockchain, because every node is somebody else replicating your data. So for example, I think JP Morgan is replicating JPM coin across like 5 different business units, and they're using it for their payment system right now. So sort of like that, only instead of 5 nodes, you can have hundreds of them. And we're also on AWS Marketplace. So our insurance client is using the permission blockchain to create a data shared pool among it and its other co-insurance people. So right now, when they settle a large insurance policy, let's say it's for an airline, for example, if you have a large claim, it's going to be 17% paid by this guy and 25% paid by this lady, and all of those settlement claims right now they send each other in paper. Like they mail the paper, and then somebody has to key them in. So this is a huge technological leap for this, and the eventual goal of this system is to actually have these payments settle automatically using the blockchain system. So this is why you might want to use a permissioned blockchain instead of a database. And then Chainweb is our public blockchain, which we launched testnet in March. And so Chainweb uses the idea of proof of work and Bitcoin and Nakamoto consensus in order to settle transactions, and it is a permissionless system that works all around the world. But because of the way Chainweb works, and usually I give like an hour-long talk just on Chainweb, so I'm not going to talk about how it works. You're just going to have to take it that it works, and we can talk about it later. But there are many chains that all run at the same time, and everybody uses all of the chains freely and equally. It's not like I own this chain and you own that chain. It's all part of the same network. And we think that proof of work, if you can figure out how to scale it, is a great solution for the kinds of activities that you want to do on a proof of work chain, on a public blockchain. You can have people buying tokens that represent real value anywhere in the world. You don't have to worry about settlement. You don't have to worry about borders. You don't have to worry about when the market is open. And if you could figure out how to put real data without exposing yourself onto this public chain, then you could actually figure out how to make distributed applications that make real value. So, for example, we have a fintech client right now, and they are a company that has made ETFs for many years, and they are using our technology to use AML KYC on the permission blockchain and tokenize a real asset, like a very conventional asset, and then sell those tokens for people that clear their AML KYC on the public blockchain. And so this, you have safe custody of your personal data, but you get to have your cake, eat it too, with reduced fees, settlement times. You can connect to investors all over the world. You can have global access. You don't have to wait to trade until the market is open. These are all benefits that you can get from trying to connect both sides of the application, both permissionless and public. So right now we have an insurance company client, a healthcare client, real estate stuff, fintech stuff, banking stuff. If you can actually have smart contracts that you can trust, that you want to put in your application, we're finally starting to see people using blockchain for real exciting application development. So this year we are launching Chainweb at the end of the year. We are, between now and then, we have a series of milestone testnets that we're planning on rolling out. So if you're interested in mining or testing the testnet, come talk to me later. We have a Pact developer community. We're rolling out all of our videos on how to use Pact and how to do the kinds of things that we want people to do in terms of application development. And we're working on a bunch of projects. And if you'd like to know more about them, I can talk about some of them. I can't talk about most of our client names because enterprise NDAs, but I'm happy to tell you whatever I can. Yeah, that's it.
So let's dive into that Nakamoto. That's what I wanted to get into next. I didn't even think about that. People are always like, oh, who's building on Cadena? Who's working with Cadena? We don't know, blah, 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 blah. Nobody's ever brought up the fact that they have NDAs with enterprise clients, and none of us even know anything about those. When I say that Cadena is so far ahead of what we even think is possible, like they're playing chess. That's probably why they don't care about half the shit we're talking about. You know what I'm saying? Like we're over here worrying about a wallet, and they're probably over here getting down with enterprise grade clients. What is that? Man, I hate when I start in a notebook and I like don't know where, like I got shit everywhere in it, so I just like start flipping through pages and writing shit down. Oh, I could probably figure it out. Nakamoto.
Hello, fixed income and financial risk management guys. In this video, what I'm going to do, I will start talking about Nakamoto consensus. I'm not going to finish because I'm going to continue talking about this in the next video. But what I want to do here, I want to explain what was the main breakthrough that as I see it, of Satoshi.
Let me see if I can get a better one that's English. We'll come back to that.
Blockchain, the hype word of 2018. But do you know how a decentralized peer-to-peer system with no authoritative figure makes decisions? The answer lies in consensus.
What is Nakamoto consensus? Nakamoto is the last name of Satoshi Nakamoto, the pseudonymous founder of Bitcoin. The Nakamoto consensus is a novel way for a bunch of computers that don't trust each other to agree on a certain shared truth. In Bitcoin, that truth is the Bitcoin ledger. Who has what amount of Bitcoin and what Bitcoin has moved from one place to another. Because in Bitcoin there's not one place for the ledger to be stored, instead every person on the Bitcoin network has a copy of that ledger, we need to agree on which one is the truth. And the way that Nakamoto consensus works is whoever has expended the most amount of proof of work wins, which means whichever ledger has had the most amount of electricity consumed to produce it will be the one that we all agree is the truth.
All right, we'll go back to that guy. He had the best one so far. So,
But what I want to do here, I want to explain what was the main breakthrough that as I see it, of Satoshi Nakamoto when he invented Bitcoin. Okay, so first we want to understand from the perspective of computer science, why do we need banks? Okay. So think about what does it mean to have financial transactions. Okay, so you have basically your own bank account here, and here you basically have two types of operation. You have basically credit, debits, and you have credits. Okay, now who is responsible for seeing, the order of transactions? Okay, the bank is responsible for it. Okay, so it means that when I am your employer, I'm depositing the money into your account, the bank records the transaction. Okay, so the bank looks when the transaction was done, and it basically what you have in your bank account is basically a record of transactions. Now, one thing, and this is basically plus or minus, and we do not care what was this transaction for. Okay, we just say that it's plus or minus, and basically those transactions went to somebody else. They went to a third party. And who is responsible to check whether you have money in your account or not? It's the bank. Now, let's assume that you do not have a bank. Then what is the problem? What is the big problem of not having a bank? Then you have something called double spending attack. And what does it mean to have a double spending attack? Okay, this is Alice. Okay, and she buys a product from Bob. Okay, and she buys a product from Kai. Okay, she buys two products. Now, she has the products are cost $50. Okay, both products are cost $50. She has only $50 in the account. There is no bank. And then what she's going to do, she's going to send $50 check to Bob and $50 check to Kai. Okay? Now, let's say that Bob's product went in and Kai's product went in. And now they want to collect the money, but they cannot collect the money because it's $50 here. Okay? You don't know who does it belong to. Does it belong to Bob or to Kai? Now, for a bank, there is no problem because a bank will see that this, let's say that the $50 came first from Bob, okay? Bob comes, the check arrived to Bob first, so he will come and collect the money, okay? The bank will record from plus $50 here. It will say that $50 went to Bob and then zero. When Kai will come to collect the money, it will be zero. Okay? So the bank as a central authority has only one role and one role only. The role of a bank, okay, is to order transactions. Basically, keep a ledger book. Of course, the banks have other functions that they fulfill in the society, like issuing credit, okay, giving you mortgages. But in the initial role of a bank, okay, when people deposit money into the bank, they count on the bank to basically keep a ledger book. Okay, that's the main role of the bank. Now, Satoshi came after 2008. And he decided that he doesn't trust the banks because the banks, in his opinion, created the crisis. And because, in his opinion, okay, the frictions, when you have basically a payment system through the bank is too complicated or is too long. For example, if you want to order an oil tanker from Saudi Arabia, okay, you have to go through a lot of hoops. You have to issue letters of credit. It's a very complicated
Who the fuck is ordering a fucking tank?
process, okay? And it's a very complicated process because the banks,
When homie's not teaching blockchain, he's ordering tanks.
have a monopoly. And the government, according to Satoshi, not according to me, it's according to basically the philosophy, the underlying philosophy as I see it, okay? Basically, you know, banks have monopoly on this, okay? And he didn't like it. So what do you do in order to circumvent this, okay? I'm not going to go now into the nitty-gritty stuff how he did it. We're going to talk about this in the next videos. But the major observation of Satoshi was that if you declare transactions publicly, the problem goes away. So in other words, if everybody know your ledger, if everybody are aware of your ledger, if everybody know that you have $50 in your ledger, okay, then those kind of attacks are gone. Because everybody are watching you. They see all the transactions and they know all, not only a bank, but all people know, okay, that Bob got your check before Kai. Okay? The key observation of Satoshi was that if you have something like this, if you make all transactions public, okay, you don't need a bank. You don't need a centralized authority, okay, that orders transactions, because transactions will be automatically ordered because everybody sees them, okay, and then if there is an argument, the majority will decide, okay. Let's say that I, went to facilities and I didn't see Bob, Alice sending the check to Bob. I just see that Alice sent the check to Kai. And Bob, I didn't see the transaction, okay? But when I come back and I see that, you know, that actually Bob tries to collect the money, I said, no. I didn't see the transaction. I just saw this transaction. But then most of the people that didn't use the facilities, okay, which observe all the transactions, say, no, Yaakov, you're wrong, okay? We will decide because we are the majority. So as long as the majority is not bribed, okay, that Alice didn't bribe all of them, okay, against Bob or Kai, you will know, okay, the majority will decide. It's a democracy. The majority decides that this is basically the correct transaction, okay? So that's the idea behind what we, okay? So that's the idea behind what we call the Nakamoto consensus. Now, we are going to talk in the next videos, which I'm going to record a little later, okay, about the underlying pinnings of how do you do that, because it's not an easy thing to do. And even, you know, and even
Dude, this
many
guy's on
people
point, man.
that know math and computer inside out always, you know, they're kind of, it's a very clever trick. And I actually recommend you guys to read the Bitcoin paper and see how Satoshi himself is talking about it. Okay, that Bitcoin should be a payment system. Okay, he created this to circumvent the banks, or to circumvent the current money, you know, the current payment system, which actually involves, in his opinion, a lot of frictions. Okay, he created this system, and he actually clearly states, it's in the paper, which basically says that Bitcoin is a peer-to-peer payment system. Okay, just like you share files between each other, his idea is that we can actually share money between each other. Okay, so this is actually the main observations that I see that underlies Bitcoin's, you know, Bitcoin's function and Bitcoin, and how Bitcoin works. Okay, so how it is implemented, okay, all this blockchain stuff and all that, we will talk about this a little bit later.
Gosh, I hope he's got it. Please tell me this guy has another video, man. Damn, this guy's killing it. Hell yes. Oh my gosh, how does this guy only have 1,000 subscribers? Damn, this guy is so effing good. I wonder if I can get him on the show for an interview. So where is Nakamoto consensus? We're looking for 3 years ago. This 2017 was 6 years ago, 5 years ago. Damn, this guy's a freaking genius. All right, so there's Nakamoto. Public key cryptography in a nutshell. There we go. This one confuses
Okay,
the shit out of me.
This is a very special video for me because this is the first time that I'm recording something which is not directly related to courses, okay? But I think that for your benefit, for the fixed income guys' benefit and for the financial risk management benefit, I couldn't resist but record it. So I'm going to talk about Bitcoins now, okay? And I know that a lot of you are not mathematically savvy, so what I want to do first, I want to talk about public key cryptography. And this is going to be a layman introduction to public key cryptography, okay? Because what I want to explain how this magic is done, and for me it's absolute magic, okay? Because it's actually very counterintuitive that you can actually ensure or verify signatures, okay, without, by basically publicizing them in public. And for me, it was a very challenging thing to understand how it is done. But then I found a great metaphor, and I want to share this metaphor with you. So what is a public key cryptography? Okay, so if you have Alice and you have a Bob, okay, what you want to do, you want Bob or C, which is Meikai, okay, they send messages encrypted in a way that only Alice can decipher them. So think about how amazing it is, okay? You guys can encrypt those messages, and if somebody stands here in the middle, okay, and he intercepts the message, he cannot do anything. He cannot read the message. Only Alice can do it, okay? This is called public key cryptography, or PKC. Why? Because this is like a revolutionary concept that was invented in the 70s by RSA, Rivest, Shamir, Adelman. But apparently it was invented before by some dudes in the British intelligence. And it was just deciphered recently. It was unclassified like in the 2000s. And we then discovered that, somebody, actually invented this RSA algorithm in the British intelligence or American intelligence, the NSA, the United Kingdom NSA, 20 years before RSA. Like in the 50s already, the Brits probably knew what's going on. Okay? Now, I do not want to speak about how does it work. I just want you to understand the principle behind it. So we're not going to talk about computer science at all. We're going to talk about, how it is done without computer science, how this can be done in a regular email, because this can be done in a regular email, and I think if you understand this example, you'll be able to understand how this PKC works in general. Okay? So how would you do it in a general email? So basically, you have here Alice. Okay? And here you have Bob. And here you have Kai. Okay? Now let's assume that you do not have computers. Okay? How Alice can ensure, okay, that Bob and Kai can send a message to her that only Alice will be able to decipher. Okay? So so if Alice is going to send them a simple stamp, a press stamped envelope, for example, that Bob and Kai will be able to put the letter into this envelope and send it back, it won't help. Why it won't help? Because me or somebody else will be able to intercept this envelope, tear it apart, okay, take the letter, read it, and and find all the information that Alice has. Okay? So how do we prevent it? Okay? So here's the examples that you need to think about when you think about public key cryptography. So if you want to have a secured message that only Alice will be able to read, what you are doing, okay, you're sending an open safe to Bob, and you will send another open safe to Kai. So you will have two copies of an open safe, okay? And the safe code only Alice knows. So what will Bob or Kai will do? Bob and Kai will have this open safe. They will take this open safe, okay, and they will put a letter inside, and they will shut down the safe. Tick, 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 right? Only Alice has a key to this safe. Bob and Kai do not have. They just randomly do the keys, and the safe is shut down. So they close the door, okay, and now the safe is locked. And what they do now, they send the safe back in a regular mail, safe back in a regular mail to Bob or to Alice. Okay? So now they have a regular mail that goes to Alice. That's brilliant. Because now, if me or somebody else will intercept the tape, we shut down. The safe code only, you're sending an open safe to Bob, and you will send another open safe to Kai. So you will have two copies of an open safe, okay? And the safe code only Alice knows. So what will Bob or Kai will do? Bob and Kai will have this open safe. They will take this open safe, okay, and they will put a letter inside, and they will shut down the safe. Tick, 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 right? Only Alice has a key to this safe. Bob and Kai do not have. They just randomly do the keys, and the safe is shut down. So they close the door, okay, and now the safe is locked. And what they do now, they send the safe back in a regular mail, safe back in a regular mail to Bob or to Alice. Okay? So now they have a regular mail that goes to Alice. That's brilliant. Because now, if me or somebody else will intercept the tape, it won't help. Because we will have to decipher. Okay? And if the code is very tough, we won't be able to decipher. Even if we have, even if we have somebody that is a professional in opening safes, if the code is very, very tough. Okay? That's exactly, ladies and gentlemen, what happens in this picture. So what we do in public key cryptography, we have a problem, a math problem, okay, which is very tough to solve. So Alice, okay, publishes parts of the problem for Bob and Kai. Okay, it is just like publishing an open safe to Bob and Kai. Bob and Kai, okay, takes the letter, put it into this problem, encode it with this problem, and send it back to Alice. This is just like shutting down the tape. Okay, you can think about maybe even, okay, I have a file that I'm sending, okay, and now when I'm encrypting the file, only Alice can open it. Okay, that's exactly what's happening, ladies and gentlemen. So if I'm here, or if a U.S. government here, or if somebody here, and they intercept the message, they have no chance of reading it. Just like here in this example, if I'm intercepting the safe, I'm having a safe, but it's useless to me because I cannot open it. Okay, here is the same story. Okay, and if you understand, if you understand this safe problem, if you understand this safe concept, you can understand public key cryptography. It's exactly the same, but it is done with computer science. Okay, and the idea behind it, okay, is to have like hard math problems that one way is easy and another way is hard. So for example, one problem like that is taking a number and decomposing it into 2 primes. So if you have a number, okay, and you know the 2 primes, which which comprise it. For example, if you know that 10 equals 2 times 5, it is very easy to verify. However, it is very tough to verify, okay, or for big numbers, it is very tough, given 10, to decompose it into 2 times 5. This is easy for small numbers, but for large numbers, it is very, very, very tough. We do not have an algorithm to do it. We do not have an efficient algorithm to do it. We have good algorithms, but they still take much more time, much more time. So this is like similar to here, okay? If Alice knows the code to the safe, okay, it is very easy for her to open the safe. But for these guys, or for me, if I'm intercepting the message, it will be very, very, very tough to do it. Why? Because I do not know the safe code, so I can spend 20 years, 30 years trying to open the safe code. Okay? So that's the essence of public key cryptography. Now, one thing that you want to actually, to actually remember, that it also provides a way for digital signatures. Because how do you know that Alice is Alice? Well, Alice is Alice if she can open the tape. She can open the safe. Consider the following example. Let's say that the only way to open the safe is through fingerprint. Okay? So Alice sends the safe to Bob and Kai. Okay? And Alice and Bob and Kai put the letter back, and then they send it to Alice. And now Alice opens the safe and reads the letter. Okay? So and how does she open the safe? Now, this is a very sophisticated safe. You can do it only with your fingerprint. Okay? So by reading the letter, okay, Alice verifies that she is Alice because only her fingerprint can open the safe. So here, this is how the digital signatures work. Okay? By basically providing keys, by basically reading messages, you verify your own identity. Okay? So this is actually very, very, very interesting concepts, and they're all coming from this kind of comparison between encryption, public key encryption, and safe. And public key encryption is based on what we call math problems, or trapdoor math problems, where where one way is easy, another way is tough. And one example like this is taking a number and decomposing it into two primes. Thank you very much and have a great day.
I could hear his phone going off the whole time. Dude, this guy is so freaking smart. What time? Are we at 2 hours yet? We got enough time for one more. Damn, dude, this guy is on point, man. Oh my gosh. I just learned so much in 2 videos that blew my mind. I can tell what people are in here that are just kind of going through the motions and what people are taking this seriously. Good for the ones that are, guys. I'm proud of you guys. This shit's not easy. Take a look at, I wanted to know that other one. I wanted to see the private key encryption one. But it doesn't look like he's following these up in any order. All right, Merkle trees is a huge one. This guy, if I can understand Merkle trees after this guy's video, I'll be like a kid on Christmas. This one threw me through a loop. I didn't understand this one at all. I was hoping Doug was going to teach me this.
Now let's talk about Merkle trees. That's a continuation of the previous video. Okay, so why do we want Merkle tree? So the idea behind Merkle tree, okay, is to actually create a device where you can actually very quickly spot whether whether the trees, whether the data is actually reliable or not. Okay, because for example, if you have a tree like that, okay, how can you guarantee that whatever the data that you have here, okay, is actually, the data that you started with? Let's say you have 1 here, and now I'm, as a hacker, I'm going to come, and instead of 1, I'm going to put 0, okay? And what you want to do, you want to guarantee that if somebody tampers with a tree or tampers with your data, you'll be able to catch it immediately. You'll be able to catch it immediately. So one way to do it is a device which is called serialization. So what you want to do, you somehow want to encode the data of the entire tree inside one, in one way, so that it will be actually a very efficient way, to actually see whether the data is being tampered or not. So one way to do it is what we call serialization. So how does serialization work? Let me just show it to you. I'm not going to explain it formally. Okay? Serialization is just when you have the data and you just concatenate this into a string. So for example, if you have a folder, and inside folder you have the list of files, let's say Yakov 1, Yakov 2, Yakov 3, and Yakov 4. So serialization, okay, is going to be something like that. You will take Yakov 1, and you are going to concatenate it with Yakov 2. And here you are going to concatenate it with Yakov 3, and then you're going to concatenate it with Yakov 4. That's all there is to it, okay? So if you have a folder system here, and you have files, okay, and you do not want anybody to tamper with these files, so what can you do? You can actually serialize it. Now, if I'm coming back, okay, and I'm going to say, okay, I'm now going to change this guy from Yakov 1 to Yakov 0, what will happen? Well, this string, is going to refer to the old files, but the new string is going to be Yakov 0, Yakov 1,
Okay.
Yakov 1, Yakov 2, Yakov 3, and Yakov 4. You see? So now, Yakov 1 and 0 are going to be different, and voila, you know exactly that somebody, changed the name of a file. Okay? You don't know what file it changed. Well, now you know. You know here because you kind of have the thing, right? So here you have an additional benefit that you know exactly what file it changed. Okay? So this is called serialization. Now, this is a horrible way to hold, to hold information. Why? Because here, for example, you don't know, which belongs to which. For example, I can say here, Yakov 1, 2, or something like that. So then it will be Yakov 1, 2 here, okay? But then you can actually get confused which string belongs to which file, okay? So this is not a good way to store data. This is a much better way to store data. But this is a great device to know if somebody tampered with your data or not, okay? Now, Merkle trees are a very similar concept. But first of all, instead of serializing the folders or the file names, as I did here, you are going to serialize the entire tree. And how do you serialize the entire tree? Well, it's actually very simple. Let's say you have 0, 1 here, and then you have 2, and here you have 3, and here you have 4, and here you have 5, 6. Okay? So when you serialize, you go from the bottom top. You can also go from the top bottom, okay? Nobody prevents you to do it, but, and that's how I talked about this in class, but the classical implementation of the Merkle tree is going from bottom, from top to bottom, from bottom to top. So here, for example, the serialization is going to be 0. Here it is going to be 1. Here, the serialization is going to be 0, 1, and 2. Okay? Because the 0 comes from this child, 1 comes from this child, and 2 comes from this child. Now, what about this part? Okay? So in this node, you will have 0, 1, and 2. What about this part? Well, here you are going to have 5, 6, and here 4. So the serialization will be 4, 5, 6. And when you are going to here, it is going to be 0, 1, 2, 3, 4, 5, 6, for example. Okay? So the serialization on the left-hand side comes first, then comes the node, and then comes the serialization in the right-hand side. So if you think about this, okay, we had basically for quicksort, we had print left, print node, print right. Okay, so when you want to serialize, you can say, okay, serialize left, concatenate with node value, okay? Maybe I'll use another color. So serialize left, concatenate node, and then concatenate serialize right. Okay, and once again, if you are touching any one of those guys, just like with the subfolders, right, you can actually say that you know that somebody tampered with your data. So for example, here, it is going to be 0, 1, 2, 3, 4, 5, 6. Now here, I'm changing it from 0, I'm changing it to 20, for example. So then it is going to be 20, 1, 2, 3, 4, 5, 6. And you can see that this and this are different. Okay, so you know that somebody tampered with your data. Once again, it is a horrible way to organize data because these are strings. You don't know, you cannot find your legs. You don't know here, right, if it's 0, 1, 2, 3, 4, 5, 6 came from this node, or maybe it was, 1, 2 here, so, and 0 here, so you have 0, 1, 2, 3. I mean, you can see that it's not a good way to organize data, but it's a very good way to see if you're tampering with the data or not. If you tamper with the data or not. Okay? Now, suppose you do not want to expose the content. Here, the problem with this serialization is that you kind of expose the content of the tree. Okay? Now, for security purposes, as we talked about, if you don't want to expose the content. So what do you do then? Well, then you use cryptography. As we described in class, there is this concept of trapdoor function. Where you have data, this is your data, and you apply this function, you get a mumbo jumbo string. It is very hard or almost impossible to go from this string to the data itself. It is impossible. I mean, it's possible, and maybe you guys can discover how to do it, okay? Because we do not have a mathematical proof that it's impossible. But until now, the best minds in computer science, best minds, best mathematicians, blah, 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 couldn't do it. Anybody that can do it, he is going to become very rich, and he's going to hold the world, or at least the security, in his hands. I cannot say in a public video what he's going to hold of other people, but you can actually imagine what he's going to hold. Okay? So this is called, now an example function like this is called SHA. Now I told you, okay, for laymen, you can think about this as being, for example, something like this. Okay, that if you have a number x, it is very easy for a layman to square it. Anybody can square it, okay? Everybody knows that 5 times 5 equals 25, okay? But to take the square root for a layman and not for computer science as a mathematician, because they will laugh. They watch these videos, they will laugh into my hands and say, oh my God, what you're talking about, taking square root is very easy if you know the Newton method, right? But it's somewhat non-trivial for people from, from business community or CEOs. You give them 5, they will square it. But, okay, you ask Bill Gates what's the square root of 5. Oh, my God, oh, my God, oh, my God, right? Well, maybe Bill Gates knows, but somebody else doesn't know. Okay? Is this clear? So, this is easy, but the reverse is much tougher. Okay? This is exactly the same story, but it's now much more sophisticated because it's not just for laymen, it's for the smartest people in the world. So if you give the data
one more time,
or at least
this is the SHA, this is their
security,
algorithm.
almost impossible to go from this string to the data itself. It is impossible. I mean, it's possible, and maybe you guys can discover how to do it, okay? Because we do not have a mathematical proof that it's impossible. But until now, the best minds in computer science, best minds, best mathematicians, blah, 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 couldn't do it. Anybody that can do it, he is going to become very rich, and he's going to hold the world, or at least the security, in his hands. I cannot say in a public video what he's going to hold of other people, but you can actually imagine what he's going to hold. Okay? So this is called, now an example function like this is called SHA. Now I told you, okay, for laymen, you can think about this as being, for example, something like this, okay? That if you have a number x, it is very easy for a layman to square it. Anybody can square it, okay? Everybody knows that 5 times 5 equals 25, okay? But to take the square root for a layman and not for computer science as a mathematician, because they will laugh. They watch these videos, they will laugh into my hands and say, oh my God, what you're talking about, taking square root is very easy if you know the Newton method, right? But it's somewhat non-trivial for people from, from business community or CEOs. You give them 5, they will square it. But, okay, you ask Bill Gates what's the square root of 5. Oh, my God, oh, my God, oh, my God, right? Well, maybe Bill Gates knows, but somebody else doesn't know. Okay? Is this clear? So, this is easy, but the reverse is much tougher. Okay? This is exactly the same story, but it's now much more sophisticated because it's not just for laymen, it's for the smartest people in the world. So if you give the data and you apply the SHA function, you will get a mumbo-jumbo string. Now here, okay, another way to get, one more step to get to the Merkle tree is just to take a SHA. Okay? So what you do now, instead of taking 0, 1, 2 here, you will take a SHA of 0, 1, 2, okay? And here, you're going to apply a SHA to 0, 1, 2, and 3. So basically, you are just going to make sure that it's mambo jumbo, mambo, 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 jumbo, right? Nobody will be able to guess it. Now, if you
Do you guys understand how he got the Shah? Did anybody get what, like, how is it getting mumbled jumbled? Yep, I get Shah's the algorithm, but where is the algorithm getting created for? No. What is the method? The Shah is just the method of the Merkle tree? We'll go into that. Let's see if maybe he'll explain it to us.
start with the same data and you're applying these SHAs, okay, sequentially, you'll get the same data at the end. Okay, you'll get the same SHA at the end. However, if I tamper with the data here, okay, and I will get a different SHA. So if I will get a different SHA, I know that the data has been tampered with. I don't know where, and I don't know how. Okay? I know that it's been tampered. Right? Now, this SHA algorithm, this Merkle tree algorithm, okay, is the heart of Bitcoin. Now, the one thing that Bitcoin has, instead of having a binary tree, it has a very simple list, like this. Okay? In each list, in each element of this list, right, just like a tree, it contains transactions. But it will also contain a SHA that will be basically a SHA of everything that came before that and this guy. So how does Bitcoin work? Exactly, we're going to explain in the next video. We're going to discuss it next lecture, okay? But just to make sure that you understand that the Merkle tree, that that there is a direct linkage between Merkle tree and this kind of lists that Bitcoin has, and this, because each list contains transaction, it is called a blockchain. But in reality, if you have a folder system, right? Let's say that here you have one folder, contains a lot of stuff. Now there is another folder, so it has files, plus maybe it has subfolder. So this subfolder contains also files and some other subfolders. Okay? You can think about these subfolders as being basically the blocks. And then the files will be kind of the transactions which corresponds to, which somehow correspond to Bitcoin, to financial transactions, which is what Bitcoin is. Okay? And then if you apply, now here you have only one subfolder. That's what will correspond to Bitcoin, to this list. If you have more than one subfolder, then it's going to be a blockchain tree if you want. Okay? And there are people that are using blockchain tree, but we are not going to talk about this right now because we are not interested in the nitty-gritty stuff of how blockchain works yet. We will be interested a little bit later. Okay? So, I hope that this kind of clarifies what Merkle trees are, what lists are, and we also about SHAs, right? It's these functions that one direction is easy, another direction is hard, okay? And it kind of clarifies what's going on with all these technologies that was invented by Satoshi. So basically what we're doing, we're looking on these small pieces of puzzle. And the genius of Satoshi was that he actually put them together. He didn't use anything that wasn't known before. The brilliance of this guy was that he realized how to put these things, all these things together in order to create a decentralized system that actually kind of secure. Okay, and we're going to talk about this next lecture. Okay, so have a great weekend. And
Dude, this is what's up, man. This is where it's at, guys. Legit. This guy's the real, this guy's got it. This is one of the best teachers in blockchain that I've ever found. I'm so glad we came back to his video. I already got like 5 pages of notes. And I'm just getting started. We'll pick up on this tomorrow and just keep running down this rabbit hole, dude. This is awesome, man. You guys understand why I'm teaching you guys this? Does this make sense? Does anybody in here not understand why we're learning this? Yeah, no way, right, Dane? This is why I say if you educate yourself on what blockchain technology is, you have it up 100x on any retail investor that comes into the space. The more you understand how these blockchains work, the more that you understand how the technology works, the more you can see the difference between when somebody comes out with something like the snowball compression algorithm and they start talking about subnets and subshards. You're not over here thinking that, you know, Avalanche is going to scale to the moon, right? You actually could look at the technology and go, that's a joke, you know? And this is hard to do by yourself. Like, I don't know if I could be doing it without you guys, you know, because it's so hard to sit. It's like watching paint dry, because in theory, Santino's comment just threw me off there. You don't have to come here, Santino. You can unsubscribe, homie. I don't even know what I was saying now. I guess we'll wrap it up with there, guys. All right, love you guys. Thank you guys so much. Hopefully you guys have a great night. We'll pick this one up tomorrow. Love you guys.